Hi, everyone. Today I'm going to provide some new perspectives to the thermal evolution of the moon. And I will start from introducing several heat source problems for the moon for different time scale, different components. And then I'm going to introduce and propose that tidal heating might be the potential solution. And then I'm going to show what we have done, the model for the thermal evolution of the moon. The main motivation of this work is trying to understand the unexpectedly slow cooling of the RMO lunar magma ocean, and also the billions of years extended merry volcanism erupted from the lunar mantle, and also prolonged lunar dynamo, which recorded by the paleomagnetism for the core. For the first problem of the lunar magma ocean, the left panel shows the canonical crystallization sequence with different accumulates. For its temporal evolution history, Borg and Carson 2022 reviewed the radiometric dating results. The data points in the right figure can be related to different stages, different accumulates, or different processes. And the background red color corresponds to the age spectrum for the old detrital zircons. There are two main points here. The first point is that all these ages of different stages and the peak age for the zircon, they all align around about 4.34 billion years. So they are concentrated. The second point is that if the moon formed around 4.5, then the age of 4.3 means it might took around 200 million years for the RMO to solidify. So it was a prolonged process. If we are going to consider the energy state for the RMO, it looks like this is saying that the first thing, it is non-linear. There was a transition at around 4.3 billion years ago. And before that, it was a high energy state. And then after that, low energy state, but sustained for a while. Then for the energy state for the lunar mantle, let's look at the age frequency distribution for the merry volcanism. The figure here shows the result. Basically and intuitively, it is also non-linear. And for here, there was also a transition time of about 3.3 billion years. Before that, high volume eruption. And after that, it maintained a low volume eruption, but sustained for billions of years until at least, for example, 2 billion years ago, the age of Chinese Chang'e 5 basalts. As the moon is small and it was presumed that the moon should cool very quickly. And the sample analysis result from both Chang'e 5 and Chang'e 6 basalts show that there was no enrichment of radioactive elements in their mantle source to release heat. So until now, the heat source for this prolonged merry volcanism is still a problem unsolved. Lastly, let's look at the energy state for the lunar core and lunar dynamo, which was recorded by the lunar paleomagnetic field. The data point here showed the paleo intensity evolution with time. And I put the histograms of the age of merry volcanism as a background. As we could say, coincidentally, they look very similar. They both shared a transition time of about 3.3, 3.2. So it was also non-linear. And unfortunately, until now, it is still very hard to find a heat source to explain both high intensity and the longevity of lunar dynamo. But it looks like from here, both for the lunar mantle and the lunar core, they both shared the non-linear evolution history and also have a low energy state and sustained for billions of years. Then the question is how to explain all of this stuff. We propose here that tidal heating, lunar tidal heating might be the key. Lunar tidal heating refers to the conversion of orbital or rotational energy into heat through internal friction caused by periodical deformation under gravitational forcing. For example, for the moon, as the moon was squished, deformed by the Earth periodically, this deformation and accompanied energy dissipation can generate internal heat. And during the early time, when the moon was much closer to the Earth, this phenomenon can be more prominent. Actually, lunar tidal heating has been studied during the Apollo era. The paper of Peel and Carson, 1978, they modeled the the tidal heating for the solid moon. The red figure here shows their result. The x-axis is the Earth-Moon distance, y-axis is the heating rate. They found that lunar tidal heating rates decayed very quickly and early, and they came to the conclusion that tidal contributions are probably not important. This is a highly cited paper, and they did a really great job in modeling. So it looks like after this one, the consensus was lunar tidal heating for billions of years was just negligible. But as we have, this model is based on the assumption that the moon became fully solid very quickly, for example, within 10,000 years. But now we have more sample returned from the moon, and with new data, it looks like the moon have experienced prolonged thermal history. So that makes us to look back on tidal heating of the moon and to think about what's the case for example, partially molten moon or weakened moon, at least locally. And even during that time, there was one paper pointing out that these conclusions may have been too quickly reached. And they also pointed out we have to consider more choice of physical parameters for the moon. But unfortunately, this paper has only been cited for once. So let's do that for a partially molten moon. The figure here shows the relationship between tidal heating rate, the red curve, with temperature, the bottom, and the melt fraction, the top x-axis, and also the blue curve is the viscosity of the system. It turns out both at the high temperature end and the low temperature end, tidal heating rates are just minor, while in between, when the system maintains a partially molten or mushy state, tidal heating rates can increase a lot. The physical mechanism under this is that when at the high temperature end, the system behaves like liquid, so it flows very easily under deformation, but it is hard to sustain internal friction to generate heat. While at the low temperature end, the system behaves elastically, so it is hard to deform the system. While in between, when the system switches from a liquid-like to a solid-like behavior with intermediate viscosity, and those solids were surrounded by melt, the system can be deformed. And it can also dissipate energy. Then the tidal heating can be increased a lot, orders of magnitude. So this is saying basically there should be a temperature range or a melt fraction range for the system to maintain this enhanced tidal heating. Actually, this is not new. This theory has been applied to the study of tidal heating, for example, of Io, icy bodies like Europa, Enceladus, and outer solar system bodies, and even for the Earth. But it implies that, for example, for the RMO, a melt fraction like 0.6 to 0.1 can significantly enhance tidal heating. While for the lunar mantle, localized melt fraction, for example, smaller than 0.05, although the tidal dissipation rate is decreased, but it can support those Mare volcanic eruptions, depending on how much energy you require. So we developed a parameterized thermal evolution model for the moon, highlighting the contribution of tidal heating with Professor Harriet Law, who is an expert in tidal research. I'm going to get into the detail of the model. Here are some preliminary results for both RMO and the Mare basalts. So in the left panel, we could see, as we consider this enhanced viscous tidal heating, the heating rate has the possibility to be higher than radiogenic heat and sustained for hundreds of million years. So basically, this is saying it can reproduce the first stage of high energy state. And as the system cooling down and the melt is going away, the tidal heating rate starts to decay very quickly. So both in the heating rate and in the melt fraction of the system or temperature, we could see a cliff, just like what we observed in the sample. And we also modeled that for the Mare volcanism, for the mantle. Basically, and we explore different parameters with different cooling rates. Basically, the conclusions are just similar. We can reproduce enhanced tidal heating rate higher than radiogenic heating for billions of years. And the cliff can be reproduced at some point. So basically, it might be a way to reproduce this nonlinear evolution history that we observed. And it looks like this can work both for the RMO and for the Mare volcanism. So what's the takeaways? We propose here tidal heating might be a promising heat source for the moon, especially for the early evolution for billions of years. And it looks like it might can help explain both what we observed for the RMO and the Mary volcanism. And for the last time, because of the time limit, I do not have time to get into the details. But I want to propose here and highlight here, and also we already account for that in our model. The thermal evolution of the moon might have been coupled to the tectonic evolution of the Earth, especially during the late Archean, when the moon was much closer to the Earth. If you have interest, we can talk about this after my talk. That's all. Thank you.